This video clip is the number 3 clips for the chapter 4 of the analysis of statically determinate beams and frames. Previously, from the past 2 video clips, we review how to analyze statically determinate beam, the procedure of that analysis, starting from consider the beam or the frame and draw the free body diagram, and the number of unknown in the free body diagrams are gonna be equal to the number of the equation of equilibrium we have. And then after we determine the reaction, we draw the portion of the beam that's cut as a given point, and then at the cutting point we will have the normal force, shear force, and bending moment due to the applied load. And then we use the equation of equilibrium again. We can determine the normal force, the shear force, and the bending moment. However, when we move to the another location, the value of the normal force, shear force, and the bending moment usually change the value. So for this kind of changing, we need to see how the shear force change along the length of the beam and the frame. That means we draw the so-called shear diagram. Okay, and also we like to see the change of the bending moment along the length of the beam and the frame, and we draw the bending moment diagram. After finished drawing, we can determine the maximum shear force, and we also can determine the maximum bending moment, and later we may design the beam and the frame based on the moment max and based on the maximum shear force. Okay, and if we cut the section and then we set the coordinate x, for example, as variable. By doing that, from the second clip, we can determine the function of the shear force and the function of the bending moment. By that function, we can draw again the shear diagram and the bending moment diagram, and we can find Vmax and Mmax. Anyway, if we consider the last example from the previous clips number 2, we have the beam with 3 segments. That means if we use to draw the shear diagram moment diagram based on the equation of the shear forces and the equation of the bending moment, is going to take quite a long time, and it is sometimes inconvenient. So we come to our next section. We are going to use the relationship between the distributed loading or force. We represent it by W, with the shear force is the V, and the bending moment the M. Okay, by using this relationship, our drawing of the diagram going to be easier, and this method is called graphical method. Okay, let's take a look at the beam in front of us. It has the pin support at A, and it has the roller support as D. This beam is the statically determinate beam. It's subjected to what? It's subjected to uniformly distributed load. No, sorry, the distributed load here is not uniform, and the point load F1, F2 and F3, and also the moment M1 and M3. Okay, under the application of this kind of loading, the beam by itself gonna defect, and then we can cut the beam at the X, and then we consider a small portion of this beam with the small length of delta X. When we cut this, since the beam is in equilibrium under the apply of loading, this small portion of the beam also be in equilibrium, and if you extend a little bit further, this is going to take the uniformly distributed loads in this small area acting on it. Okay, and then you cut this portion of the beam, you can see that the uniformly distributed load will have what is so-called the resultant acting on it. And then on the left hand side and the right hand side, we're going to have the internal shear force and internal moment. And on the left, if on the left the value of the shear and the moment is V and M, when you move this to the section on the right, the value of shear and moment will change, as I mentioned before. So what the relationship between them? Okay, let's first consider the beam segment under the uniformly distributed load. But before we go that, let me recall you something that we have the conclusion from the previous clip. First, we have the relationship of dV by dx equal to minus W. What the meaning of that is, we have the slope of the shear diagram equal to minus of the uniformly distributed load. For example, we have this one, dV by dx and equal to minus W. That means we draw the shear diagram, we take a look at the given beam, and then we have another one is the dm by dx is equal to what? Is equal to shear. We have this relationship. It said the slope of the moment diagram as a given point is equal to the shear force at that point. That means when we draw the moment diagram, we take a look at the shear diagram, and we draw the shear diagram, we take a look at the distributed load. That shows some relationship between them. And also, if you may recall, the force, okay, the force at that given point is going to produce the change of the shear force at that point. If the force is downward, the change of the shear forces, the delta V, gonna be negative. Okay, and also if we take a look at the moment from the previous clip, the clockwise moment at a given point on the beam will produce the increase of the bending moment at that point. And to make it in opposite, if the moment is in the counterclockwise, the counterclockwise moment will produce the decrease in the moment on the moment diagram at that point. Anyway, we can prove all of this by consider the small portion of the section of the beam and to make or to confirm our note that we conclude from the previous clip. Let us come to consider a small portion of this beam segment again, and under the application of the uniformly distributed, the distributed load, we are going to have the shear and the moment, and the shear with some change in shear, and the moment with some change in moment, as I mentioned before. And if you consider the summation of the force in the vertical direction equal to 0 and set the upward is positive, so this V gonna be positive, and this V plus delta V gonna be negative, and the resultant of the distributed load also gonna be negative. So we get the equation of V minus the resultant of the distributed load and minus V plus delta V. So this V will cut with this V, and then we have delta V equal to minus W delta X. And if delta X gets smaller and smaller, this equation will change to this dV by dx, the slope of the shear diagram, equal to the negative of the applied distributed load, as we concluded before. By this equation also, you may write this equation to be dV equal to minus W dx. Okay, and then if you integrate this from, let's say, from A to B, okay, you also need to integrate this from the A to the B, and then you will get this as V sub B minus V sub A. This is the change of the shear force between A and B, and it's going to be equal to minus of the integration from A to B of the force and then dx. Or if you write it clearly, you get this as the change in the shear force equal to minus of this integration. When we're talking about the integration gonna be the area, okay, area under the function, So we can conclude that the change of the shear forces is equal to minus of the area of the distributed force. Okay, and then when we take the moment at the point O, point O is here, you will get the counterclockwise. Okay, if this counterclockwise is going to be what? It's going to be, sorry, this is going to be, okay, this is going to be counterclockwise, is going to be positive. And then if you take the moment here, this force gonna produce zero moment, and this we gonna have the rotation in the clockwise direction. When this one is clockwise direction, it's gonna have what? It's gonna have this length delta x, and it is negative. Okay, and m here also is going to rotate in the same direction as the v, so it's negative. And the last one we have is the m plus delta m. It's going to be positive. Okay, and the moment due to this resultant force also in the same direction as the m plus delta m. So this guy is positive and this also positive. So when you do the computation, you may get the delta m equal to this. To cut this, okay, with this one equal to the v times delta x minus w. Sorry, this is supposed to be k. This will be k delta x square. And since delta x can be very small, when we consider it to be the differential, the equation can be reduced to dm by dx equal to v. This is as we have before, and it means the slope of the shear diagram is equal to the shear force at that point. And then if you do again the dm, okay, is equal to v dx, like it in this form. And if you do the integration from the a to the b, and also from here from the a to the b, you will get the m sub b. This is gonna be m sub b minus m sub a. The change in the moment between b and a is gonna be what? Integration of this is going to be the area under the shear diagram between point A and point B, or you may like the equation in the form like this. Okay, these two relationships are the same as we found it from the previous example. And then for the beam with the point load, we consider the small segment of the beam again, but this time we have the force F. Okay, at the force F, we can consider the change of the shear and the moment by summation of F sub y equal to 0. By summing like this, and upward is plus, so this is plus, this is minus, and this is going to be minus. And then the v, okay, cut the v, you may get the delta v equal to minus f. That means what? That means the downward force F produce what? Produce the negative of the change in the shear force at that point. Okay, if this is 10, the shear force between on the left and on the right of this line gonna change downward or negative by 10 kilonewton. And again, if you consider the effects of the external moment, this external moment also provides the change in the moment. And if the delta x is small, okay, we can consider this as the what? Take the moment about this point, and then what we have is what? The counterclockwise is positive. So what we have, when you have counterclockwise is positive. If counterclockwise is positive, this is going to be minus, right? This is going to be clockwise minus. Oh, sorry, this is going to go together, and this is going to be, this term going to be the same, and it's counterclockwise. So this is positive, and this change to m palm. Sorry, this change to m palm, and m palm is in opposite, so m palm is negative. And also the m is clockwise, the M is negative. Okay, and the force, the shear force, going to rotate this way. So the shear force also provide negative moment. And then the M here will cut the M here, and your equation will be what? The delta M minus M palm and minus V delta X. Since the delta X going to be very small, because we only consider the point over there as a line cross here. So the delta X going to be very small. When delta X very small, this term just eliminated. This term must be eliminated, and then we have the change of the moment from the left to the right at this point. If the moment is clockwise, the change gonna be increased, okay, by the given moment. However, the shear, if the shear downward, okay, the effect gonna be decreased. But if the force is upward, the delta V gonna be increased or positive. So we have the conclusion here. The conclusion, the first one, the slope of the shear diagram at a point is equal to minus of the loading, the distributed loading at this point. And second, the slope of the moment diagram at a point is equal to the shear force at that point. And next, if we write this equation and do the integration, we have the change in the shear force between 2 points is equal to the negative of the area under the distributed load between those 2 points. And then if we rewrite the second equation and do the integration, we have the change in the moment is equal to the area of the shear force, the area of the shear force between those 2 points. Let's say between A and B, the change in the moment between A and B is the area of the shear diagram between the A and B. And if we have the point load that X downward, that's X downward, the shear diagram at that point will decrease equal to the magnitude of the force. And if it's upward, that means it's going to be increased, okay? And the sixth, if at the point where the clockwise moment acts, the moment diagram will be increased by the magnitude of that moment. So to use the graphical method to draw the shear diagram and the moment diagram of the beam or frame, we're going to use these 6 relationships, and I should separate into 2 groups. The first one is the 1, 3, and 5. These 3 relationships will be used for the shear diagram, and the other, the 2, 4, and 6 is going to use for the moment diagram. Okay, let us do some conclusion by a small consideration. Again, go back to the previous clip and trying to remember the 3 examples, and we can get a conclusion that if the distributed load is polynomial with degree n, we will see that the shear force will have the degree of n plus 1, and the moment gonna have the degree of n plus 2. Okay, let's recall our previous example. This beam has no uniformly distributed load in this area, so the V in this area gonna be like constant. Okay, because what? Because the dV by dx equal to 0. Okay, and also this portion gonna have constant V, right? And for the M of the M, you will get the M of this beam, like this. And then the M is going to be linear function. The shear going to be constant. That is going to be 1 more degree from what? From W. And the moment is 1 more degree than the shear. It's going to be like this. And next example, when the W is the constant, this constant of 50 kilonewton, so the shear gonna be linear. If you may recall, this one, the shear is gonna be linear. Okay, if you draw it like this, and the shear gonna be something similar to this. It's the linear function. And also the moment diagram is gonna be have the shape like this. That means the constant distributed load produce the shear with 1 more degree to be the linear function, and produce moment with 1 more degree of the shear force to be the quadratic function. Okay, and the last one, we have the beam subjected to what? This beam is subjected to triangular loading. When we have triangular loading, the distributed load is linear function, so we have the V as the quadratic function. Okay, and we have the moment as the cubic function like this. So 1 more order. When we have the loading, the shear force gonna have 1 more order higher, and the moment also have 1 more order higher than the shear. Okay, by this conclusion is going to help you a little bit when you draw the shear diagram and moment diagram. The example, let us consider the cantilever beam. It have the fixed support here. Okay, and by fixing this support and have the free end here, we have 3 unknown force and moment at the support. We may have this one as the A sub x, and summation of x sub x equal to 0. This A sub x automatically equal to 0. Okay, and then by this free body diagram, you may see that this one will have the uniformly distributed load. Okay, over here, and the size of this is going to be 400. That is 400 Newton per meter, and then time what? Time 1.2. That is going to time 1.2. Then you may get this guy to be what? To be 480 Newton, which is the resultant of this uniformly distributed load. And it's act at what? And it's act at the centroid of this area, okay, which going to be half of 1.2, and this is going to be about 0.6, okay, 0.6 meter. And then if you do the summation of f sub y equal to 0, what do we get? What do we get? By letting the v upward is positive, okay, and then you're going to have v, this v is upward, this is going to be v is upward, and the 600 is downward, equal to 600. And also the resultant force from the uniformly distributed load is going to be downward, so it's going to be 600 downwards plus 480 downward, so the result is going to be what? 1080, right? 80, the unit of it is the Newton. And again, it's going to be this. And what's going to be the moment over here? The moment is counterclockwise, is positive, so the summation of the moment at, let's say, A, okay, equal to 0, as I mentioned. Let's say this is the A, and then this one V sub A, and this one gonna be M sub A, and then we have the what? Counterclockwise at the positive, okay, and we have M sub A is counterclockwise is positive, and then the moment from 600 gonna be in opposite, so we have of 600 times what? 600 times the whole length of the beam, that means 600 times 2, 600 times 2, okay. And the resultant from this uniformly distributed also rotate in this direction, in the opposite, so it's gonna plus 480, and 480 gonna times the 0.6, okay, and when you do the computation, you got M sub A of 1588 Newton meter. Okay, next we draw the shear diagram. We put the X in the horizontal direction, and this gonna be 0 meter, and this one going to be what? Going to be the point here. This is going to be 1.2, and this is going to be 3. And by having these 6 equations, we may use this one, we will use this one, and we will use this one for the shear diagram. And from the start, we start from x equal to 0 until x equal to 3. And then at x equal to 0, you may see that we have the what? The shear here in the vertical direction. So we have this one for sure, upward, for 1080 Newton. That means we start by this one, and then here we come from the point A inside it, and then we find what? We find what? We find the what? We find the distributed load. Okay, When this distributed load is 400, so our dV by dx gonna be minus 400. So this one gonna have the curve like this, minus 400, minus 400, and minus 400. The slope here gonna be minus 400 and minus 400 until here. And what the value of the shear here? The phi over here. We'll compute by using this one. The phi here minus 1080. Okay, the phi here minus at the A, and it's going to be equal to the area of the load and negative. So it's going to be equal to this area. Let me select the other color, this area. Okay, it's going to be this area and negative. So we have this one of minus of what? Minus of 480. This area is 480. And then when you move, this one gonna be phi equal to 1080 minus 480, and then you got that for 600. So you get this 600. So we have the constant slope of negative 400, and the value there is 600. And when you pass the uniformly distributed load to another area, okay, another area, and let's see, we move to this one. So this area has no uniformly distributed load. That means this term gonna be 0. And if this term is 0, the slope here gonna be in the line here gonna be in horizontal, and slope is 0. The line here is gonna be horizontal. And finally, if you arrived at the end of this, you got the force of 600 Newton and downward, and you use this relationship, and the shear gonna be down here for 600. This is the shear diagram. And for the moment diagram again, now we have the 1555 here. That is the moment at the point A. That means we start by taking this, and since the moment here is counterclockwise, so the value of the moment here going to be negative. So it starts by minus 1588. And then the shear at the point A is what? The shear at the point A is 1000, okay, 80. So the slope here, the dV by dx, must be positive. Okay. However, the value of the slope decrease to 600. Okay, over here, the slope here gonna be less. So we have this one is 1080, and over here supposed to have less. Okay, slope gonna be 600. What the value of moment here? The moment here is what? Is minus of what? Of minus 158. Okay, and the moment at this point minus the moment at this point equal to what? Equal to the area of the shear diagram between that's 2 points. So it's going to equal to 1/2. 1/2 what? 1/2 of 1080 and gonna plus 600. That is 1680, and then it's gonna time 1.2. Okay, and the result is gonna be minus 580. And next we move to this portion of the shear diagram, and the slope gonna be what? Gonna be plus 600 and plus 600. And the moment here is what? The moment here is gonna minus the moment here is gonna minus 580, and then it's going to equal to what? It's going to be equal to the area here, the area here, the area here. The area here is going to be what? The area here is going to be 600 times what? Time the distance here is the distance is going to be 0.8. So what we have is equal to 600. Sorry, this color is wrong. Gonna be this one. Gonna be 600, and then time 0.8. And you may have this is going to be 60 times 8. Okay, 60 times 8 is going to be 480. So the M is going to be equal to 480. Sorry, 480. And then this is minus plus, move to the right. It's going to be minus 580. And then you get the moment here of minus 100. So we get a minus 100 here and get a curve here. And finally, what we have is the end, the free end here have the clockwise moment of 100. So if it's clockwise, this moment diagram gonna move upward, and the moment diagram close. And we finish the shear diagram and bending moment diagram of this beam like this. And then we may go to the next example. Okay, this example is for the simple beam. Previously, we considered the cantilever beam. This simple beam, we have the pin support at A. So the free body diagram here supposed to have the A sub x here. But since the summation of x sub x equals to 0 and no horizontal force, so the A sub x is 0. And next we have what? We have the B, and the B is the lower support. So we have the B sub y here, B sub y, and over here we have the A sub y. We can determine the value of A sub y and B sub y. Let us summation of the moment about A equal to 0. And what we have is we take the moment here, the A sub x and A sub y produce no moment, and B sub y gonna rotate what? In the counterclockwise direction. So we have the counterclockwise as the plus. Okay, and it's gonna time what? The moment arm between B and A is what? This is going to be 10, 15 and 20. So we got 20 times what? Times B sub Y. And then it's going to be what? Equal to, this moment is in the opposite direction. Okay, it's going to be equal to 4,000. Okay, and the moment from 600 kilonewton also rotate in this direction, and it's gonna time what? This is gonna be time the distance of 10. So we plus 600 time 10. So that's gonna be 10,000. So our B sub Y gonna be 10,000 divided by 20. That is going to be 500 Newton. Okay, kilonewton, sorry, kilonewton. And if you do the summation of F sub Y equal to 0, and then upward is positive, what you get is the A sub Y is upward and the B sub Y is upward. So this A sub Y plus what? Plus 500. And then you get what? Upward. This is downward, equal to 600. So we get the A sub Y equal to 100 kilonewton. Okay, let's show you how to determine the reaction. And then the shear diagram again, we put the X along the horizontal axis. And then we get this one 0 meter. This one gonna be 10. And this one gonna be the total of 20. And the shear is in the vertical direction. Okay, now in the shear diagram, we're gonna use this, guys. We're gonna use this one and also this one. And at point A, we have the 100 kilonewton. So by following this equation, when we have the point load here, that point load is gonna move like 100 kilonewton up. Okay, up. That means increase. And then we have this for 100. And then when you move between A and C, there is no W. The W here is 0. That means what? That means the slope of the curve between this portion gonna be 0. So we're going to have slope of 0 here, and the value of the shear force along this region is gonna constant of 100 Newton. And then we go to the point of 600 kilonewton. At this point, what we have is the force gonna take this one downward. Okay, and the downward is going to be what? 600. And then the value of here is gonna be like minus 600 downward, and then you have plus 100 already. So the shear that going to be here is going to be minus 500. Sorry, it's going to be minus 500. Is here, it's minus 500. Okay, and there is no uniformly distributed load between C, D, and B. So all of this is constant. When you arrive here, the B sub Y is up, following this is going to cross this for 500, and we get the value here of 0. For the moment diagram, the A is the pin, and the A is the pin, and the C is the pin. So that means there is no external moment. The moment here is 0. The moment here, the value of moment here also 0. And this is 0 meter again. And this is going to be 10 meter. And this is going to be 20 meter. Again, we use the rest of this equation. The dm by dx equal to v. That means we have the v of 100 across this. So for sure, we will have the shear slope that equal to the shear. The slope here, gonna be what? Gonna be 100. So the s, the slope here is going to be 100. Okay, and then what? The value of the moment here is going to be what? The moment here, the value here, and minus 0. And then it's going to be equal to, the area here. Let me select also color the area here. The area here is what? The area here is going to be 100 times 10. So that is going to be equal to 100 times 100 is the side of this. It's going to be 100. And then time, 110 times 10. We are going to have this of 1,000 kilonewton meter. So we have this one as the 1,000. And then we move to the region of CD. Okay, we move to the region of CD. Again, now we have what? We have the shear of minus 500. So the dm by dx equal to v. So the slope here is changed from plus 100 to minus 500. So we get this. And what is going to be the value of moment here? Again, it's going to be m. And then it's going to minus 1,000. Okay, minus 1,000. And then you guess it's going to be equal to the area here. That is going to be minus 500 times 5. So it's going to be minus 500 times 5. That is going to be minus 2,500. So the m here is going to be minus 2,500, and then plus 1,000. So the result gonna be what? Minus 1,500 here. Okay. And then at the point D, we have 4,000 kilonewton meter, which is clockwise. When this one is clockwise, so this moment going to increase for what? Increase for the value of 4,000. So we have plus 4,000, and then we are going to minus this by 1,500. So it's going to be what? Plus 2,500. So this is going to be 2,500. And then again, the slope here is going to be minus 500 here. Okay, and then we have the moment diagram as shown here. What are Vmax? Okay, following this we can determine our Vmax. Our Vmax gonna be minus 500. And what is the Mmax? The Mmax gonna be plus 2500. So we may use this maximum moment to determine the section of this beam, and then we can check the section can resist the maximum shear force or not. Okay, next we have this. This picture show again the simple beam with roller at A and pin at B. And if you determine, you can find the resultant force like this. So let me skip the portion of drawing the free body diagram of the beam and the portion of using the equation of equilibrium to find the resultant force. Let us has the resultant force of A 5.75 and of C or 34.25. And by doing this, again we draw the diagram by putting the X, and this one is 0, this one gonna be 5, and this one gonna be 10. And by doing this is upward. To use this should be upward for 5.75. And then since it is no uniformly distributed load along here, so the slope here is gonna be 0, and this is gonna be 5.75. Okay, up until this point there is the 15 kilonewton downward force. So that means this one must go downward for 15. So this one will move for this by 15. Okay, the value here gonna be what? We are gonna be plus 5.75, and then it's gonna minus 15. So you get this of minus 9.25. And then if you move further to past B, you will get the W of 5 kilonewton. So the slope here gonna be what? Gonna be minus 5. And what the shear here supposed to be, if you don't know, the V there minus 9.25 minus 9.25, and then is equal to minus of the area under this uniformly distributed force. Okay, so it's going to be minus of what? Minus of 25. So this one is going to be minus 25, minus 25, and then the V that we have is going to be minus 25, and this minus and minus is plus. When you move this one is also minus 9.25. 0.25. So you will get this V as minus 34.25 and kilo Newton. Okay, and then you get this one, and finally you get the upward of 34.25. So this one will go upward here and cross here. This is the shear diagram, and with the Vmax of 34.25. And then for the Mmax, and for the moment diagram, the C gonna have zero moment. However, at the A we have the 80 kilonewton, and if you consider the 80 kilonewton here, it's going to be clockwise. So the 80 kilonewton here gonna produce plus 80 kilonewton at point A. Okay, before that, let's us check. The slope here is 0. The slope here is minus 5. We have this of plus 80 due to what? Due to this one, and then it is clockwise. And then we move to the portion AB, and you see the portion AB has the shear of 5.75. So the slope over here is going to be 5.75, and it's up. That's going to be what? Going to be the point here. What the value of this one? This one going to be m, and then minus 80. The moment here, by using equation, the delta m, the moment here minus 80 is equal to the area, under the shear diagram. Let's put this one. So it's going to be the area here. The area here going to be 5.75 times 5. Okay, we will get the positive 5.75 and times 5 equal to 5.75, and then it's times 5. What you get, you put all of them in the calculator. This 80 gonna move up to sum, okay, with this value, and then we get this of 108. The value is going to be kilonewton meter and meter. So you get this, and when you move here, this shear force change, from plus 75 to minus 9.25. So the slope of this curve is going to be minus 9.25. So you get the slope there of the S equal to minus 9.25, and then the moment at point C, the moment is 0. So this is going to be 0 moment for sure. And then what's going to be the slope here? The slope here going to be this value. The S is going to be, slope is going to be the value of the shear. So you can draw the line from the slope of minus 9.25 to slope of minus 34.25, which is a lot larger. So the curve is going to be curved downwards like this. Okay, that is the slope for the segment AB, and this is slope at B, and this is the slope at C. Okay, let's come into this again, and let me go faster. We get the reaction of the beam already. The A sub y is 500, sorry, the A sub y is 750, and the C sub y also 750. And then when we come to this, what we have is, this is 750, right? When this is 750, we have this one, so this shear gonna increase by plus 750 due to the shear force at A. And then here you come to the uniformly distributed loads region. On this region is 5 meter, and the value of W is 100. So SO here is gonna be minus 100. Okay, it's going to be minus 100, and then minus 100 until you arrive in this point. Okay, and what's the value of the shear at this point? So the shear here is going to be minus the shear here, minus the shear before, minus 750, and then it's going to be equal to minus of the what? Minus of the area here. The area here is what? It's going to be 5 times 100. So the area here is going to be 500. 5 times 100 is 500. Okay, so the V is going to be 250. Okay, and kilonewton. This is the value of shear here. And then during this portion, there is no distributed force, so the S is equal to 0 up until this point, just to this point. And then this is gonna be 250 also on the left of this force. And then we arrive at a 1000. So this 1000 is downward. It's gonna be minus 1000, and then plus 250. That is gonna be equal to minus 750. Okay, that is going to be minus 750, and there is no uniformly distributed load about here, so the S is equal to 0, or the value here is minus 750. Up until here we got this one of up 750, so the shear going to be 0 here. Okay, that is the shear diagram in which we have the maximum shear of plus 750, and also we have minus 750. That's for the Vmax for this beam, plus and minus 750. Go to the moment diagram. If you draw the moment diagram, you consider the shear diagram. Okay, and there is no external moment at this support. So at this support the moment is 0, and what we have is what is the graph. Okay, since this one is 0, we come here, we got what? We got the shear of 750. Since we got the shear over there of 750 dv by dx equal to 0. So the slope here is gonna be 750. Okay. And over here, if you may recall, the value here is 250. So the slope here on the left is gonna be 250. And how about the value of this point? The value of this point you may determine by m minus 0. M here minus 0 here is equal to what? Is equal to the area under the shear diagram. That is going to be the area here, and you can determine this area, right? How much is going to be this yellow area? Okay, we can compute it by equal to 1/2 of what? Of 750 plus 250, 1/2 of 750, and then plus, okay, 250, and time what? And time this distance of 5 meter, and time the 5. So this is 1,000. This is 1,000. This is time 5 is what? 5,000, and divide it by 2. So the moment here is gonna be 2,500. So the moment is gonna be 2,500 here. Okay. And next, the slope is going to be equal to the value of shear here. So all the slope that's along the second region, you get this as what? As the S equal to of them 250. And then when it's up to this, what the value of the moment that's gonna occur here? So again, I put this one, and then it's gonna be m, and it's gonna be minus m over here, m over here, m over here, m over here. Is gonna minus m over here. That is minus 2,500. And then it's going to be equal to the area that we have. This one, the area. This area is the green area here. Okay, and that is going to be 250 times 5. So that is going to be equal to 250 times 5. That is going to be 1,250. And then when you move, the m is going to be what? 1,250 plus 2,500. This is going to be 3,750 kilonewton meter. Okay, it's going to be 3,000. That is going to be bad writing. I'm going to buy a new pen for this. 3,750. And then the last one, the shear here is minus 750, and you have the slope equal to the shear, so the S here is going to be minus 750, and the value of the moment at this support gonna be 0, since it is what? It is the roller. So we get the shear and the moment as shown. Okay, the last one for this beam. This is a quite complicated one, and you can see the A is the pin. The A here is a pin, and we have the pin at A with external moment, and C and D and F all roller. So the total number of reactions gonna be 5, and we cannot consider the whole beam together. Too much unknown reaction. So we need to separate this beam into 3 portions. The first one, see the first one is EF, okay, link by joint E. The second one is BCDE, and the last one is gonna be B, G, and A. This is the light blue, the yellow, and the green. So we start by the green. Okay, this portion of the beam have the F as the point load. So we have the reaction here. Okay, now let me paint all our beam, and then we can go further easily. This is the yellow, and this is the light blue. Okay, and the reaction here is F sub y, and at E we're going to have E sub x and E sub y. And if you see this beam, you also see that this beam has no horizontal force. So summation of x sub x equal to 0. So E sub y is 0. And again, this beam is symmetry along this. Okay, this means half of the force in this portion will distribute to the E sub y, and another half gonna distribute to the F sub y. So this half of the force gonna distribute to E sub y, and maybe this another half. Okay, the light blue distribute to the F sub y. So what the size of this is going to be 3 times half of this is going to be 2 meters. So E sub y going to be 6, and F sub y also going to be 6 and kilo Newton. Okay, we have that. And then the E sub y and E sub x gonna act at point E of this portion of the beam, and this portion has C sub x and C sub y, 2 unknown, and B is also the pin. Since B is also it's the hinge, so B gonna have 2 unknown, B sub x and B sub y. And you may see that the yellow portion going to have 4 unknowns. And if you have summation F sub x equal to 0, the B sub x is going to be 0. But then we cannot solve this portion of the beam because too much unknown. So we move to this portion of the beam AB. And then the reaction at A sub x and A sub y going to be here. And we have 1, 2, and 3 unknown. Summation of x sub x equal to 0. This is 0. And now we may take moment at point A. If you take moment at point A, what we have is the B sub y gonna rotate in this direction, counterclockwise. Okay, and if V sub y times what? V sub y times the distance of 5, and it's counterclockwise, so it's gonna be, sorry, this one gonna be positive. So this B sub y times 5 is negative because it's counterclockwise, and then you set clockwise as positive. And this guy, and this side gonna rotate clockwise. Okay, 15 times 3, and the last one also the clockwise. This is clockwise. This is plus 8. So we get B sub y of 10.6. And if this is 10.6, this B sub y also 10.6. And then summation of f sub y equal to 0. We are going to determine the A sub y. A sub y is upward. 10.6 here also upward. So they are plus. And minus 15 here. So A sub y is 4.4. Okay, coming back to the yellow portion of the beam. So we have C sub y and D sub y as the unknown. We take moment at the what? At the C. Okay. When you take moment at the C, what we have, the D sub y gonna rotate like this. That is gonna be positive. D sub y times what? D sub y times this distance is going to be 2, and then we have 10.6 rotate the same as d sub y. So this gonna time what? This also gonna time 2, and they are plus. However, coming into this 6 kilonewton, this 6 kilonewton have the opposite rotation. It's gonna time what? It's gonna time the distance of this, which is 4 meters. So we get the d sub y of 1.4. And finally, summation f sub y equal to 0. The 1.4 d sub y plus c sub y, you get this. And then 10.6 and 6 are downward, okay, negative. So we get c sub y of 50.2. Okay, and we are ready to draw the shear diagram. Let's take a look at this. When we draw the shear diagram, we will see the what? We will see the problem. And then we have the reaction 4.4 here, so the shear here up 4.4. And then between A and G, no horizontal force, so the slope is 0. So all of this is 4.4 until the left of point G. At the point G, the 15 kilonewton point downward, so that is going to be minus 15. From what? From the plus 4.4. Then you got this is of minus 10.6. And since there is no W between G, B, and C, and then the slope along this line gonna be 0 and 0, and up until here to here on the left side of point C, the value of shear is minus 10.6. And do you guys recall the C sub y? The C sub y gonna be what? if you go back the c sub y, the c sub y is 15.2, and that means the 15.2, let's use this one, the force will push along this by the value of 15.2 up until here. So this is going to be plus 15.2 and minus what? Minus 10.6. Minus 10.6. And then you get this of 4.6. Okay, and since the CD also has no load, distributed load, so the slope here is 0. And then we have the resultant over here. Anyone can remember that? The resultant there, that is going to be 1.4. So coming over here, the value of this shear, let me move this one, is going to be 4.6 plus 1.4, and it's going to be 6 kilonewton meter. Sorry, 6 kilonewton. And this is 6 kilonewton. And the slope over here is 0. Okay. And then we come to the portion of the beam that has the uniformly distributed load. So the slope here gonna be minus 3 all the way. And this is 6. And what's going to be the shear here? That is going to be minus 6 equal to minus of what? Minus of the area here. Okay, the area here is going to be 3 times 4. That is going to be 12. That is going to be 12. So if you move here, it's going to be minus 12. And then UV is going to be minus 12 and plus 6. Your life here is minus 6 kilonewton. And finally, at point F, you have the resultant force of 6 kilonewton. And now your resultant force cross your shear diagram here. Okay. Next, the moment diagram, and we start again from point A, and then the point A have what? The point A has the moment clockwise. Since moment of clockwise of 8 kilonewton, that means the moment here gonna be plus 8. Okay, and then when you draw the moment diagram, you got to take a look at your shear diagram. This shear diagram has the shear force of 4. So the slope over here will get S equal to plus 4. And the value of the moment here gonna be what? It's gonna be M here. And then over here is plus S. It's gonna be minus 8. And then it's equal to the area of the shear diagram between the 2 points. So this is going to be what? This is going to be 4.4 times 3. Okay, we have is equal to 4.4 and then times 3. You put the 4.4 times 3 into your calculator. 4.4 times 3. That is, oh sorry, 4.4 times 3 is going to be 13.2. So that is going to be 13.2. This is going to be 13.2. So our M is going to be equal to 13.2 and then plus 8. So you will get it as the 21.2. Okay, and then you move to the next section, and what we have in this next section is V equal to minus 10.6. So S here is going to be equal to minus 10.6. Okay, and the value of this going to be along this one is downward. What's going to be the M here? The M here, the M at this point. Okay, minus 21.2, and then it's going equal to what? Equal to the area over there. That is quite a lot. Okay, the area gonna be all the area here. You gonna what? It's gonna be minus 10.6 times 4. So it's gonna be minus 10.6 and then times 4, and it's going to be what? It's going to be M equal to 21.2 minus 10.6 times 4. 10.6 times 4 is 42.4. That's going to be 42.4, and then you have this of minus 31.2. Okay, you are moving to the next portion. The next portion, the shear is 4.6, so the slope along here is going to be positive 4.6. So it's going to be upward in this direction, and the M here is gonna minus, and then you minus what? 21.2, and then it's going to be the area here. The area here is what? The area here is 4.6 times 2. 4.6 times 2 is going to be equal to 6 times 2. That's M is going to be 21.2. 4.6. This is plus when we move this one going to be minus 21.2 and then plus, this is 9.2, right? It's going to be 9.2, and then you get this one as minus 12. Okay, and then you get this, and the last part of this, you move to the portion of this with the value of 6. Okay, so the slope here gonna be plus 6. Okay, and also you know that point here, point E is the hinge, and the hinge gonna have the moment of 0. So you can derive here easily to get this as the 0. So if you do this one like this, you will get this point of 0 moment. Also, I should mention that this also is a special point in which the the moment is 0, because this is the what is the, let me change this color to darker one. This is the hinge. Okay, and then the rest of this gonna be what? This is gonna be the slope of 6. The slope here is 6, and the shear is here is 0. So the slope over here gonna be 0 at this maximum moment. So this m minus 0, and then is equal to the area here. What is going to be the area here? I like let's make this one. So this is gonna be the area here. The area here is 1/2 of 6 time this distance of 2, right? So by doing that, you may get this one as the 1/2 of 2 and time 6. So you get this 6 kilonewton meter. And finally, at the F, the moment is 0. And since the shear is -6, so the slope here also -6. Okay, that is the end of these clips to explain you about drawing the shear diagram and the moment diagram by using the graphical method. And you should notice that when you draw the shear diagram, you got to take a look at the beam, and if you draw the moment diagram, you got to take a look at the shear diagram, and you have 6 relationships. They are separate 3 for the shear diagram and another 3 for the moment diagram. If you can recall, that means you are understand what you are doing. Okay, and we will go to the drawing of shear diagram and moment diagram of a frame on the next clip. Okay.